everyone. Today's notes are on the Pythagorean theorem, so we're going to be doing lesson 6.3. The Pythagorean theorem is an equation that relates just to right triangles, and so we want to start out with remembering some information about right triangles. In a right triangle, the hypotenuse is defined as being the longest side of the right triangle, and it's always opposite the 90-degree angle. Today in the notes, I'm going to use the color purple to illustrate which side of the triangle is our hypotenuse. The two other sides of a triangle that are not the hypotenuse are called the legs of a right triangle. In the first example, I've highlighted them in blue, and then I dropped off highlighting them. The first example in the notes today just wants us to practice seeing which side is the hypotenuse. And so you want to remember that it's always the longest side, and it's going to be the side that's across from the 90-degree angle. Sometimes one way that students like to see which side it is they draw an arrow out from the 90-degree angle, and the arrow points at the side that is the hypotenuse. So in this case, segment RS is the hypotenuse, which means that segment RT and segment TS are the two legs of a triangle. Quick note about geometry notation. That little line without the arrows at the end on top of the two capital letters, that's the word segment when you say that out loud. And then it doesn't matter what order you put the two letters in, but we always name a segment with two letters that are at the end points of the segment. So in example B, the hypotenuse is segment XY. And then segment XZ and segment ZY are the two legs of that right triangle. And in the last example over here, segment QP is the hypotenuse of that right triangle, and then segment QR and segment PR are the legs. Question number 2 in the notes today is more practice with remembering and recalling information about right triangles. So you'll see in the first example, it says, given the side lengths of a right triangle, identify the hypotenuse and the legs, and then sketch and label a picture of the triangle where you put the letters and the numbers in the right order. So in the first example, segment AB is equal to 5. Segment BC is equal to the square root of 16. 16 is a perfect square, so that equals 4. And then segment AC is equal to 3. And so in that example, segment AB is the hypotenuse because 5 is the biggest out of those three numbers. And then segment BC and segment AC would be the legs. So you'll see in the picture I drew, it doesn't actually matter which way the triangle's pointing or facing, but I put the letters A and B on either side of the hypotenuse, and I labeled that side as 5. And then the C goes on the 90-degree angle. It says segment BC is equal to the square root of 16, which is equal to 4, so you can label that one either way. And then segment AC is equal to 3. So I also have the numbers on the picture. In number 2b, I'm told that segment DE is equal to 4, segment EF is equal to the square root of 36, and we know the square root of 36 because that's a perfect square, that's equal to 6. And then segment DF is equal to 5 square root 2, which you can type into a calculator to get that decimal approximation as 7.1. 7.1 is the biggest out of those three numbers, so that means that segment DF is the hypotenuse. When I draw my picture for the triangle, it doesn't matter what way the triangle is facing. I did this one on purpose to look differently than the other two did. Segment DF is equal to 5 square root 2, so we should label that side. Segment EF is equal to the square root of 36, which is 6. And then segment DE is equal to 4. And so including the numbers on the picture is part of labeling the triangle. And in the last example, in number 2C, segment JK is equal to 5, segment LK is equal to 13, and segment JL is equal to the square root of 144. And we know that one because 144 is a perfect square, so that equals 12. So out of the numbers 5, 13, and 12, 13 is the biggest number. So that means that segment LK is my hypotenuse, that side's 13. Segment JK is one of the legs, that side's 5. And then segment JL is the other leg of the triangle. That's the square root of 144, which you can label that way or you can label as the number 12. Something that's important to note about these pictures is that you have to have the letters in the right spots with relation to the other letters in the picture. Like there are definitely wrong ways to draw them, but it does not say that the triangles need to be drawn to scale. So you don't need to worry about making sure that the side that's 12 looks bigger than the side that's 5. We're just drawing a sketch of the triangles, and so putting the letters in the right places is the most important part for this one. The Pythagorean theorem is a special equation, and it only works for right triangles. And the Pythagorean theorem says that if you square the lengths of the legs of a right triangle and add them up, that sum is equal to the square of the length of the hypotenuse. And so this formula right here, the Pythagorean theorem, is definitely one that you want to memorize. You're going to use it a lot in math. So in example A, I have a right triangle, and I know that because of the box in the corner. And so I'm going to solve for the missing side length. In this one, the missing side is the hypotenuse. So a squared plus b squared is equal to c squared. That's my Pythagorean theorem that I'm going to use to answer the question. It doesn't matter whether I plug the 4 in for the a or whether I plug it in for the b, and same thing with the 8. But I do have to make sure that I don't plug either of them in for c, because c is the hypotenuse. In this example, we've decided to label the hypotenuse as x because that's the side that we're solving for, but we could have just left it as c and it would have been the same in our work. So I plug in the 4, 4 squared is 16, and then I plug in the 8, 8 squared is 64, is equal to x squared. I add up the 16 and the 64, and so I have 80 is equal to x squared. Well, to solve an equation that has a square root, you have to take the square root of both sides. So I'll square root both sides, square root, and I would be finished, except 80 is an example of a square root that can be simplified. So we want to remember what we learned about yesterday. 80 is equal to 5 times 16. 16 is a perfect square, so I can take it out from underneath the square root. And my exact answer to this question is 4 square root 5. This particular question also asks us to approximate the value of the length of the side that we're solving for. And so you can type either the square root of 80 into your calculator, or you can type 4 square root 5 into your calculator, and you'll get the same answer. It's approximately 8.9. So the length of the hypotenuse is approximately 8.9. We want to make sure we write our answer both ways. On question B, we're also solving for the hypotenuse because that's the side that's missing, that doesn't have a side length on it. So when I do the Pythagorean theorem on this one, it doesn't matter whether the 3 goes in for the A or the B, or if the 7 goes in for the A or the B, but I can't put either of them in for the C because that's the side that I'm solving for. Here I decided to leave the C, but you could put an X if you wanted to, like we did on the last one. It's the same. 3 times 3, 3 squared is 9, and then 7 times 7, 7 squared is 49. 9 plus 49 gives you 58. You have 58 is equal to c squared, and then you have to get the c all by itself because you're solving for c. So you take the square root of both sides, square root, and that's your answer to the question. 58 does not have any perfect squares that are hiding inside of it, like a 4 or a 9 or a 16. None of those numbers divide into 58. You can cut it in half, but that's not a perfect square. 29 is not a perfect square. And so the exact value for the length of the hypotenuse on this one is the square root of 58. And to approximate that, you would type that into your calculator, and you get that it's approximately 7.6. So that's the length of the missing side for B. Example C is one more example where we're solving for the hypotenuse. So again, the 2 and the 6 can go in for A or B. It doesn't matter which one they go in for. But you want to make sure that the c stays c or x because that's the hypotenuse and that's the side we're solving for. So you can't plug the 2 or the 6 in for the c. 2 squared is 4, 6 squared is 36. And then I do 4 plus 36 gives me 40. 40 is equal to c squared, so I take the square root of both sides. Probably starting to see by now that these problems all have a pattern. Now on this one, the square root of 40 would be finished, but 40 has other numbers hiding inside of it, and it can be simplified as a square root. 40 is 2 times 20, 40 is 8 times 5, but 40 is also 4 times 10. And so remember from yesterday, the reason why we pick 4 and 10 as our pair of square roots for this one, as our factor pair for this one, is because the 4 comes out as a 2, because it is a perfect square, and then it's finished. So the exact value for this one is 2 times the square root of 10. And if you do that as an approximate value, type that into a calculator, you get approximately 6.3. So in these last couple problems, what they all have in common is that we're not solving to figure out how big the hypotenuse is. Looking at example D, we're already told that the hypotenuse is equal to 13. So when I plug my values into the Pythagorean theorem, I have to be really careful and make sure that the 13 goes in for my C. Now, it doesn't matter whether the 12 goes in for the A or for the B. Here we put it in for the B, and we decided to call this missing side X in our work, and so that went in for the A. The 12 and the X could be backwards. We would still get the same answer to the question. It's important. You could just leave the X as an A, too, if you wanted to. You don't have to call it X. But see how on this one, the 12 squared gives you 144. The 13 squared gives you 169, but they're on opposite sides of the equal sign. So I have to minus the 144 from both sides, x squared, or a squared, equals 25. Take the square root of both sides. And so for this one, I get that my exact value to the question is 5, because 25 is a perfect square. 25 comes out from the square root as a 5. And so there is no approximate value because I have an exact value that's exactly 5, so I don't need to find an approximate value. On letter E, I'm solving again using the Pythagorean theorem. I'm careful to make sure that I put the 5 in for the C because the 5 is my hypotenuse, so the 5 has to go in for the C. The 4 could go in for the A or for the B. Here I put it in for the A, and then I decided to let the B stay B. So 4 squared is 16, 5 squared is 25, and then you minus the 16 from both sides. You get B squared is equal to 9. And then we'll finish by taking the square root of both sides, and the square root of 9 is 3. So for this one, the exact value is 3, and then for the approximate value, you can just write NA because the exact value is 3, so there's no need to approximate. Letter F is the last example in this section, and again, we're solving for the hypotenuse, so we're careful to plug the 15 in for my C value. The 13 could go in for the A or the B. Here I plugged it in for the B. 13 squared is 169. 15 squared is 225. Minus the 169 from both sides, you get A squared is equal to 56. And you're trying to solve for A, so you take the square root of both sides. And 56 is not a perfect square, but it does have perfect squares that are hiding within it that need to be simplified when we write our exact value. So 56, lots of numbers times to give you 56, but 4 times 14 is the one that you want to pick. 4 comes out as a 2. 14 is 7 times 2, but neither of those come out from the square root. And so you write your answer just like that. The exact value is 2 square root 14. And then typing that into a calculator, the approximate value is 7.5. So we can use the Pythagorean theorem as a different way to find the distance between 2 points that are on a graph. And so we're going to do an example of that here. We're trying to find the length from segment A. We're trying to find the length of segment AC, so the distance between A and C on the graph. And so what we can do is we can create a right triangle. In this example, we're trying to find the length of the hypotenuse, so A squared plus B squared equals C squared. The 4 and the 5 can go in for A or B, doesn't matter which one. We square them. 4 squared is 16, 5 squared is 25. We add them up. We get C squared equals 41. And then we take the square root of both sides. And so we get that the exact value for this one is the square root of 41, which when you type it into a calculator, you get that it's approximately 6.4. So we can create something on a graph and use triangles, kind of like slope in a way, to solve to find the length of the segment. And you guys, the last example in your notes today is a word problem. It's a little bit tricky because you don't get given a picture. Steve is turning half of his backyard into a chicken pen. His backyard is a 24 meter by 45 meter rectangle. He wants to put a chicken wire fence that stretches from one diagonal to the other. So it's good to know that diagonals go across shapes. So it goes from corner to corner or vertex to vertex for 2 non-consecutive vertices. How many meters of fencing will Steve need? So if you think about his backyard being a rectangle, you're trying to find the diagonal across the rectangle, which, if you ignore half of the picture, half of a rectangle is just a right triangle. And so I can do A squared plus B squared equals C squared to answer this question. Here in the picture, we've decided to name the hypotenuse X. So we put the X in over here, but you could just leave it C. 24 squared plus 45 squared is equal to X squared. So I square the 24, that gives me 576. I square the 45, that gives me 2025. And then they're on the same side of the equal sign, so I add them up. And then I take the square root of both sides. And believe it or not, 2,601, when you take the square root, it is a perfect square. It's not one of the ones we've memorized, though. You get 51 as your answer to the question. And so if he was trying to put a fence from corner to corner across his rectangle backyard, he would need exactly 51 meters of fencing to complete the job.